Okay, well, we are starting our next unit today. We're going to talk about vectors. So, a very different topic, but we are still going to be using aspects of trigonometry to help us through this. I don't have a whole lot as far as housekeeping items go. Remember, Friday is the end of the 6 weeks, so anything outstanding, if you still have a homework assignment or if you need to retake the test from last week, today was the deadline on the quiz, all of that needs to be done by tomorrow morning, 8:05. And I've had several people be coming in every day this week. If you have questions, just let me know. That's all I've got, unless anybody has any questions of their own. Okay, then we are going to talk about some vectors. All right, well, the physical world is filled with applications of vectors. For example, the speedometer represents how fast you're driving. This value is known as a scalar because speed can be defined by its magnitude alone. Only the value or number is important. So we're talking about things that are measurable. Okay. Other items such as temperature, area, mass, time. They're also examples of scalar quantities. Now, when we're concerned with both direction and magnitude, now magnitude could represent any of those previous items that we were talking about. So when we have magnitude and a direction, that's when it becomes what we call a vector. Okay, such as velocity, then we have a quantity called a vector. Vector applications appear in economics with the velocity of money, vector graphics in computer graphics, and probability vectors in statistics. So you have measurable items, but when you have that measure and a direction, then it becomes a vector. So it's a math quantity represented by an arrow that has both of those items. Now this isn't in your notes, but I think it's a good idea at the beginning. Let's just kind of run through these, and you guys are going to tell me, do you believe this is a scalar quantity or a vector quantity? Okay. First example, a boat traveling at 15 miles per hour. Why is that a scalar? There you go. We have speed, but we don't have a direction. So that is a scalar. That's measurable. It needs direction in order to be classified as a vector. Okay, what about a hiker walking 25 paces due west? That's a vector. So we have the distance he walked, but we also, more importantly, know the direction. That's a vector. A person's weight on a bathroom scale. Okay, that is a vector. There you go. The downward pull of gravity. In fact, acceleration due to gravity is a vector. Okay. In fact, this isn't a physics class, but parts of what we're going to be doing over the next couple of weeks with vectors will kind of flirt with aspects of physics. Who are my physics students? Okay, so hopefully some of this is going to seem familiar. Have you guys already gone over vectors? Okay, so good. This is going to be a review for you. Excellent. What about a car traveling 60 miles per hour, 15 degrees east of south? Definitely a vector. Okay. A parachute is falling straight down at 12.5 miles per hour. That's a vector. Okay. All right. And a child pulling a sled with a force of 40 newtons. That's a scalar. Because again, I have a force, but no direction for that force. So that would be a scalar. Okay, so you have to have both magnitude and direction in order for it to be a vector. And while you can have multiple items that can represent the magnitude, typically in here it's going to be things like the actual length of the arrow. Okay, that could be the magnitude. Speed is another one we'll be dealing with quite a bit. And also force. Okay, again, getting into a little bit of physics. Okay. All right, so really today and for the rest of the lesson, a lot of this is just the algebraic portion looking at this. I think it'll really start to connect when we get to the real world problems. We start to see how these are actually used. Okay, so you just kind of hang in there with me. But a directed line segment is the geometric representation of a vector. Okay, so this is what we have, vector right here. The starting or initial point P is called the tail or base point, and the terminal point Q, indicated by the arrow, is called the head, tip, or the terminal point. So vocabulary, notation, all of that somewhat differs as you go from textbook to textbook, even teacher to teacher. What I'm going to use is initial and terminal. Okay, initial is where the vector begins, terminal is where it ends. And you're going to know the terminal because it's going to have an arrow at that end of it. Okay, now this notation is written as V equals PQ. Now you'll notice from geometry, that little symbol up top, you'd probably go ahead and say what? Starts with an R. Ray, because it is a directed line segment, right? So here we're talking about vectors. Now, the way I was taught, I've always done it like this. If I were going to go ahead and name a vector using its initial and its terminal point, then I don't draw the entire arrow. I only draw the top portion of it. Okay, it's just another way of notating we're dealing with a vector. So the fact that I didn't put the bottom part of that arrow changes nothing. If you want to go ahead and do that, please feel free. But I just really want to emphasize that, especially if you move forward in calculus and college, you're going to see different ways of these being shown. Okay, now the magnitude or length of V is denoted as this. So it's going to look like you have double bars on either side and measures the distance from P to Q. In most textbooks, vectors are represented by boldface and lowercase letters such as U, V, W, A, and B. Now, typically, the most commonplace ones will be U, V, and W, and we know we're talking about a vector because it's going to be in bold. Okay, so some more terminology here. Two non-zero vectors, U and V, are called parallel if the lines through the vectors are parallel. Okay, so the two vectors are equidistant all the way through from each other. Parallel vectors can point in the same direction or opposite directions. A vector that is moved parallel to itself without changing its length or direction is a translation. A translated vector has the same magnitude and direction but different base points. They're still said to be equivalent. Now here's a really important term for us. A vector with its initial point at the origin is said to be in standard position. Now, we can translate a vector anywhere in our coordinate plane, but when we're dealing with them, it's really easy if their initial point is at the origin. That's what we call standard position. Okay, every vector can be translated so that it's at that point. Okay, one more little paragraph, and then we can finally get into some examples here. The term scalar is another word for real number. Remember, we were just talking about something that's measurable, and we had a lot of different examples. The product of a vector v and a scalar k is the vector that is k times as long as v. When the scalar is positive, then the product kv has the same direction as the original vector. However, if the scalar is negative, then the vector kv has the opposite direction as the vector. So here, with this particular example 1, we're talking about magnitude being the length of the arrow, the actual length of the vector. Okay. In fact, can anybody give me an example of just how you've probably seen vectors in the real world? May not have realized what they were. Has anybody ever watched the news? What am I referring to? Could use the stock market. Remember we had that mentioned before in economics. I was thinking more if you were to watch the weather. You ever seen times where they go ahead and put one of the maps up and it's just got a ton of arrows on there? Each one of those little arrows represents a vector because they could be talking about wind direction and what? Speed. Okay, so each one of those is a vector. Aiden, what were you going to say? I'm sorry? Don't worry about it? Are you sure? I worry a lot. Okay. All right. So here's the thing. If your scale value k, if it's larger than 1, it's going to result in an increase in the vector's magnitude. If it's less than 1, it's going to be a decrease in the vector's magnitude. So basically, using this vector here, I just want to draw a vector that represents those particular changes. Okay. So how would I show 2 times the vector v? There you go. So its magnitude will have been, it's increased. So it's going to be doubled. So probably something that looks like this. Now, I'm not going to go ahead and draw them exactly parallel, okay, because I'm not, that perfect. But we want to go ahead and believe that each of these that I'm drawing, they are still the exact same direction. They are parallel to each other. Okay, so there's 2v. I start from the initial, go to the terminal. Perfect. But now, what's negative 2v? There you go. Will it be the same magnitude? Yes. Now, the negative just has one job. He simply tells you direction. We saw that a lot when we were dealing with the trig triangles. Sometimes the length, one side of the triangle was negative. We weren't saying that the length was negative. That just told me what direction to go. So for negative 2v, I'm going to have, again, another vector that's parallel. It's got to have the same magnitude or length, but I'm going to switch the initial and the terminal ends. It's just in the exact opposite direction. That's what a negative is going to do to a vector. Okay. Well, let's try these other two on our own. Okay, take a few seconds to go ahead and sketch what you think 3/2 v or a negative 1/2 v is going to give you. 3/2 v and negative 1/2 v. Okay, so 3/2, would that be increasing or decreasing the magnitude? Okay, it'd be increasing, right? Even though it is a fraction, it is larger than 1.5. So probably something like this. Okay, its direction would not change because it's not a negative 3/2. So basically 1.5 what the original length was. Now, what do you think when I see negative 1/2 v? Okay, so we're going to flip the two ends because the negative changes the direction. And is it going to be a longer or shorter magnitude? Shorter. It should be half of what it was. So I'm probably thinking something like this. Now, its placement doesn't matter. I just went ahead and put it at the top. But if you were to move it down like that, it doesn't change the vector at all. Direction and the magnitude still stay the same. And that's why it's so easy for us to just move these vectors where the initial is at the origin. What do we call that? Standard position, because it's really easy to work with vectors if the initial point is on the origin. Okay, any questions so far? Easy? Okay, well, let me introduce you to something that we call component form. Component form is going to really dictate a lot of what we do and work with when it comes to vectors. Okay, if v is a vector in the plane whose initial point is the origin and whose terminal point is AB, then the component form of v is given by v equals AB. Now, this is how we denote component form. It works exactly like an ordered pair. The A moves me horizontally, left or right, depending on positive or negative. B moves me vertically, again, positive or negative for the direction. Okay? But A and B themselves, they're what we call components of the vector v. Now, you know it's not a particular ordered pair because you have those arrows on either side. So let me give you an example. Again, this isn't in your notes, but let's say I have a grid, and you'll notice I've got 3 vectors here. Let's go ahead and call, actually, let me put the terminal down here for this one. Let's call this one vector u, this one's vector v, and let's call this one vector w. Okay. Now, every vector, okay, with the exception of 2 cases, you can create a right triangle based on moving from the initial to the terminal. Those distances are what we refer to as the components. Okay. So, for example, let's say I want to go from the initial, the starting point of W, to the terminal, the tip that has the arrow, right? Well, how am I going to move horizontally to get there? How far over am I going to have to move? Was that 7? Okay, well, 6, right? And then how high? 2. So the component form for W would simply be 6, 2. The first value tells you horizontally your movement. The second value tells you the vertical movement. How do I go from the initial to the terminal? It moves just like an ordered pair. Okay, that's all component form is. But now here's something that's really, really interesting. You remember when I said we can move them to the origin? What position is that? Standard position. If I go ahead and move this vector where the initial is at the origin, it has the exact same direction, but what do you notice? What remains the same? Even if I translate it, it still has the exact same component form. I would have to move 6 right and then up 2 in order to get there. Is everybody okay with that? Okay. Well, now what I want you to do, let me go ahead and remove those. Okay. Let me move this back over here to where he was. Okay. What I want you to do now is write down for me what you believe the component forms of U and V are going to look like. Okay. Take a few seconds to go ahead and do so. Now, one question you have to answer with U is, well, what if I can't create a right triangle? Very, very similar to what would happen when we were dealing with a quadrantal back in our coordinate plane. There you go. Okay, so here's U, here's V. Let's do V first. Okay, so I want to go from the initial to the terminal. So what would the component form of V look like? It would be -2, -4. Because from the initial, I got to go 2 left and then 4 down. Okay. But now, what was the hint I was giving you about U? What would his component form be? It would simply be 5, 0. See, going from the initial to the terminal, I did move 5 right, but then I don't move vertically at all. So that would be 5, 0. That's what component form is. So these values, when you see the A and the B, A represents the horizontal movement, B represents the vertical. We call those components of the vector. Okay. Any questions? All right. Well, because we're going to be creating right triangles with a lot of these, what do you think is going to be really useful to us? What theorem? Starts with a P? The Pythagorean theorem is going to be really useful to us. Okay, so that's where the magnitude of a vector is going to come in. If point P, which is x1, y1, and point Q, x2, y2, are the initial and terminal points of vector V equals, and again, just 2 ways we can denote it, then by the distance formula, it can be shown that the magnitude of V is, okay, and you remember how I was saying at the beginning that different textbooks, different teachers are going to use different ways of showing these ideas? Okay, well, this is how we're going to go ahead and show magnitude. We're going to have the double bars, but it is possible that you may see it like this with just the single bars. I'm not going to go ahead and do that because typically if you see the single bars, people think what? Absolute value. So you have to know what context you're referring to. So everything we do in here, we're going to have the double bars. Okay. Now, here's what we want to go ahead and do. You can definitely use the distance formula if you have the points, but what you can do if you know the component form, this V1 and this V2 right here, those are the A and B distances that we were just looking at. Those are the components of the vector. Okay? And really, when you think about it, it makes sense. So let's come back over here. Let's go to vector W, back to him. Okay. Now, we know this point right here is at -7, 1. We know the terminal point is at -1, 3, right? So I could easily use the distance formula and figure out what the length is. That would represent the magnitude. But a lot of times, especially because we're going to be dealing with component form, you're going to want to use that. Okay. Well, the triangle that we created, we said we went 6 to the right and 2 up. Okay. If I did want to find the length of this right here, I mean, just think about W squared equals 6 squared plus 2 squared, right? And then what would you have to do? Take the square root. Well, look at what you ended up with. That's exactly what the formula is showing you. The square root of A squared plus the B squared. Okay. It's already set it up using the Pythagorean theorem. Does that make sense? Okay. So if I were to come back over here, well, the magnitude of W, let's see, what is 6 squared plus 2 squared? A little higher. 40. Okay. And if possible, we want to go ahead and simplify that. So the square root of 40 would become 2 square root of 10. So that would be the magnitude. In this case, we're talking about length. But remember, magnitude could really be anything. Okay. For us, most commonly, if it's not length, it'll be speed or it'll be force. Okay. All right. Well, with that in mind, let's look at an example. Example 2, given vector V, where we have point A, that's the initial point, okay, and point B, that's got to be the what? Terminal point, okay. So this is my terminal point. I want to use those to go ahead and write the component form of the vector. Now, if you've got the coordinates of both the initial and the terminal, and all you want is component form, okay, you need to take the terminal and subtract the initial. Always, always, always go from the terminal to the initial. In fact, I'm going to write that right here. Terminal subtracting the initial. Okay. Now remember, the component form is going to look just like an ordered pair, except for the arrows instead of the parentheses that we normally have. So vector V or vector AB, again, whichever you want to write. Okay. For the first part, we have to take the difference of the x's. So would it be 3 minus 6 or 6 minus 3? Has to be 6 minus 3. You must always start with the terminal point. Okay? You'll never start with the initial when finding component form. So what am I going to put for the y's? 5 minus 7. So let's see. 6 minus 3 will give me 3. 5 minus 7 will give me negative 2. That should be the component form of AB. Okay. Now, it doesn't say to do this until part C, but let's go ahead and check our work. Let's see if we're right. Okay. Point A was at 3, 7. So I'm going to locate 3, 7. So here's point A right here. Then point B was at 6, 5. Okay, so I'm going to go ahead and connect the two. There's my arrow. Now remember, the component form describes horizontally and vertically how I go from the initial to the terminal. So if I wanted to go from A to B, how far right would I go? 3. And how far down? 2. And again, in the component form, it's negative because that's representing the direction that I have to go. So that's exactly what I ended up with. Okay. This is going to work every single time. Okay. Now let's go ahead and find the magnitude of this. So remember, in component form, this is your A, this is your B. I really don't know why they used V here, V1 and V2, but it's just the square root of A squared plus B squared. Okay. Use those components to help you out. Okay. So see, how do we denote the magnitude though? Well, yeah, that's the formula, but I'm talking about if I didn't say find me the magnitude, how would I give you this? What symbol would I give you so that you would know what to do? The double bars. There we go. So it could be, you know, magnitude of vector V, or if you're using points A and B, the initial and the terminal, okay, either of those would tell me, okay, I want the magnitude. So that means the square root of A squared, so 3 squared, plus B squared. And what is that? Square root of 13. So this right here, the magnitude should be the square root of 13. So here, magnitude is referring to the length of the arrow, the length of our vector. Okay. All right. And then C, it says sketch the vector AB and the translated vector V. So we already sketched it originally. Well, when it says the translated, that means we want to go ahead and put it in standard position. So which point goes on the origin? A or B? A, the initial point. Okay. So I want to put that point right here. Well, remember, translating it will not change the direction or its magnitude. So from the initial, I would still have to go 3 to the right and then 2 down. So I know that the terminal would have to be right there. Same magnitude, same direction. Okay. It's just like we're sliding it across your grid. Anybody having a hard time? Okay. No? Okay. The last thing we're going to get to today, because this is as far as first period got, I want to go ahead and show you vector addition graphically, and then tomorrow we'll pick up with the algebra portion of this. So when adding two vectors, we draw them using the tip-to-tail method. The sum u plus v is called the resultant vector. So when you add or subtract or even multiply, I won't say multiply because when you take the dot product, you get a scalar, so never mind that. When you add or subtract vectors, when you perform an operation, you're going to end up with some kind of answer. Okay, you're going to end up with a result. So we call that here the resultant. All right. To geometrically represent the resultant, you want the initial point or tail of one vector to coincide with the terminal point or head of the other. That means I want to move these two vectors so that a terminal touches a tail. When you're doing this graphically, never put two terminals together. Never put two initials together. It has to be terminal and initial. Okay. Now the resultant is the vector that points from the tail of U to the tip of V. So let me show you how this works. Let's say I want to go ahead and show A plus B using these two vectors right here. Now you'll notice I'm going to go ahead and do this with my mouse. It's probably going to be a lot faster. You'll notice I've already got some links over here. So this represents B. See, it's the same direction, same magnitude. Okay. And I've already got one for A. Okay. So let's say I'm going to put A right here. Okay. So I'm going to go ahead. This is vector A. There it's terminal. Now, when I go ahead and put these vectors together graphically, I have to put a terminal with an initial. I can't put two terminals together. I can't put two initials together. So what I'm going to go ahead and do, because of the way this is, with the initial of B being right here, that's what I'm going to put at the terminal end, so that this is vector B. Okay. Now, you'll notice what I'm going to do, I haven't mentioned it yet, I like to use what's called the triangle method. Because, see, I've got two sides right here, don't I? If I go ahead and connect the other ends, that's going to form a triangle. That will represent the vector that is A plus B. So I'm going to go ahead and connect this one right here. So from here to here, that is A plus B. That's the result when I add vector A plus B. So we call it the resultant. And you'll see why we call it the triangle method. Okay. Now, there is another method that some other people might like. I know Mr. Heinrich likes to also use what's called the parallelogram method, where you create a parallelogram. I'm not a big fan of that. I like to stick with the triangle. I think it's very straightforward, very easy. Okay. Now, here's the thing. You can also do this in another way. You'll notice how I put the terminal of A to the initial of B? Could I reverse that? Could I put the terminal of B to the initial of A? Yeah, so let me show you that. I'm going to take this guy right here. Okay, let's say I put him right here. So that B, okay, is right there. So I'm going to take A, again, same direction, same deal. So its initial, I'm going to put on the terminal of B. So that A's terminal is right here. Okay. And I like to use what's called the triangle method. Once I've got my vectors, how I want them positioned, we'll connect them with that third side. So from here to here. Okay. So this would also represent vector A plus B. That's the resultant. That's what you get when you add those two vectors. Okay. Now, it doesn't matter how you go ahead and put them together. Take a look at what happened. What would the component form of A plus B look like? How far horizontally did I have to move? 7. And then I had to go 4 up, right? So the component form would be 7, 4. We'll do the same thing for this resultant I got just reversing. Do I still need to move 7 right and 4 up? Yeah. Okay. So as long as you're putting a terminal and an initial together, doesn't matter how you do it. You just can't put two terminals together. You can't put two initial together. Anybody have a question? Anybody confused? Okay. Well, let's try B. Okay. Now, we were talking about this a little while ago when we first started. What is a negative going to do to a vector? It simply changes the direction. So if I want to subtract vectors, think about A minus B as A plus negative B, especially if you're going to go ahead and do it graphically like we are. Okay. So let me go ahead and get my vectors back. Let me get rid of this. Okay. So this resultant and that resultant, we can go ahead and get rid of those. Okay. So I've got A, B, there's another B, there's another A. Okay, so I want to show A minus B, which is the same as A plus negative B. Well, why don't we go ahead and place B first, because he's the one that's being changed. So here's B, but Juan just told me because we're subtracting him, he's going to change direction. That's all the negative does. Now, when I go ahead and put A over to him, I just have to make sure to what? What can I put together? Two initial? I can put two initial together?
No, terminal and
A terminal and an initial. Okay, so I'm going to take this terminal end of A, and I'm going to put it with the initial of B. Okay, so let's see, here is A. Here's B. Well, how do I figure out the vector that represents A minus B? Just connect them. You finish the triangle. That's exactly right. So I would go from here to here. So this would represent A minus B. Okay. Now, just like I showed you on the first one, if I were to switch it, if I put the initial of A to the terminal of B, would I still get the same vector? Absolutely. Okay. In fact, what's the component form of A minus B? If I want to go from the initial to the terminal. Yes, sir. Uh-huh. Now, when you're creating the final triangle, that's okay. But initially, when you're putting the two sides together, you can't put the same together. That's a good question. Okay. So that's fine at the end. Okay. So if I want to go from here to here, horizontally, where do I need to go? Up one? Okay. Remember, you got to move horizontally first, so is it left or right? So because it was left, that means it's negative. So I go one left, and how high? 4. So the component form for A minus B would be negative 1, 4. The one thing I want to show you tomorrow, when we start looking at these algebraically, okay, we're going to revisit this, and I'm going to show you how graphically you still end up with the exact same answer. So ultimately, when we start doing these word problems, it's going to be up to you. Do you want to go ahead and graph it, or you just want to go with the numbers? Okay. Personally, I kind of end up going with the numbers just because I think it's faster, but you can do, whatever you like. Okay, let's try this last one here. This will be all we have for today. What do I want to do in C? I want to double A and then add it to B, right? So here's what I want you to do. While I'm taking care of this, I want you to go ahead and try that on your own. Okay? Make two sides of the triangle, one B, one double A. Find me the resultant. But for that resultant, okay, just to make sure we're all on the same page, get me the component form. Okay. So let me go ahead and erase all this right here. Let me move B back and move A back. Now for me, it's going to be really easy to double A because you'll notice I actually have two links representing A, so I can just put them together. But if you're trying to do that graphically, you could simply double what? There you go. What do we call those? Starts with a C. The side lengths that form the right triangle? Components. Simply double the components, and that would give you double A. Okay. In fact, let me go ahead and catch up to you. So both of these right here, you've already noticed, there's an A, there's an A. So I'm going to go ahead and start by doubling A. I'm just going to go ahead and put 2 together. So that is 2A. So it's still going in the same direction. There's the terminal. But now I'm going to take B over here. And remember, when you're doing this graphically, it has to be terminal and initial. Okay, you can't put 2 terminals together. You can't put 2 initials together when you first start. So I'm going to come on over here. Right there. So that this is B. See, I put the terminal of 2A to the initial of B. Well, how do I figure out the vector that is the resultant 2A plus B? What method have we been using? Yeah, just complete the triangle. Okay, we call this the triangle method. Okay, so here we go. Right there. And this would be the terminal end. This side would be 2A plus B. Okay. Now, you may have put the terminal of B to the initial of 2A. So the reason I wanted you to go ahead and find the component form was to see that no matter how you did it, you should end up with the exact same thing. Zach, help me out. I want to go from here, the initial, to the terminal of 2A plus B. How far horizontally do I have to move? I'm sorry? 9, we're close. 10. And then how high do I need to go? 8. So whether you created the resultant like I did, or if you did it the reverse, how many people ended up with that 10-8 component form? Very good, very good. Anybody having trouble with vectors so far? Any questions?
So, the last project that you did from that, the starting point for those is always like where you started?
Yes. Yes. Okay, so that's the resultant. Good, 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 good. Okay, well, let me go ahead and take this off very quickly. Why is that? I'm sure Bottrell did a really good job with this. He's a very intelligent man.
He is, but that makes the grades
Oh. Why? How did he explain it differently? He what? Okay. Okay. There you go.